Welcome to this explainer. Look, if you've ever felt that cold sweat when someone asks you to estimate the capacity of a massive, globally distributed system right there on the spot, you are exactly in the right place. Today, we're taking the dark art of back-of-the-envelope estimation and turning it into a logical, totally repeatable playbook. Here's our roadmap for today. We're going to hit 5 key areas: the architecture equation, the absolute must-know numbers, core system architecture rules, a real-world application, and finally, the ultimate goal. All right, let's jump right into Section 1, the architecture equation. To get our heads in the right space, take a look at this quote from Google's Jeff Dean. He points out something crucial. These calculations are really just a mix of thought experiments and common performance numbers. Listen, the goal here isn't to show off your math skills or act like a human calculator. It's about proving, practically, that your design is actually going to survive contact with the real world and hit those system requirements. And honestly, this brings us to our first major rule. And it's a big one. Process always outweighs precision. You are an engineer, right? Not a calculator. So aggressive rounding is going to be your best friend. Simplify all those messy fractions into nice, clean factors of 10. Also, you've got to aggressively log your assumptions so you can actually defend your constraints later on. And please, always label your units. Just writing down a 5 is a massive trap. Is it 5 megabytes? 5 kilobytes? Write it out to absolutely kill any ambiguity. Moving right along to Section 2, numbers you must know. Okay, so first up is visualizing data volume. We're looking at this expanding logarithmic funnel. Because as data scales up, going from a single tiny byte all the way up to a massive petabyte, our brains really need a quick way to grasp what that scale actually means for our system. You need to be able to instantly internalize what a gigabyte, a terabyte, or a petabyte truly represents when you're designing for massive loads. Now, this is where it gets really fun. We're translating abstract nanoseconds into visceral human terms. When we talk about latency, an L1 cache reference takes about 0.5 nanoseconds. So imagine that as a single heartbeat. Badum. But a physical disk seek, that takes 10 million nanoseconds. So if that cache read is a single heartbeat, pulling data from a spinning disk is the equivalent of a grueling cross-country road trip. To your application, that distance is literally monumental. Looking at these two diagrams side by side really drives the point home. You can clearly see the crazy extreme jumps in latency as we slide across the spectrum. On the left side, we've got micro CPU operations, stuff like a branch mispredict at 5 nanoseconds, or a mutex lock at maybe 100 nanoseconds. But as we move over to the right, to the macro operations, the scale just explodes. Compressing a kilobyte takes microseconds, sure, but reading a megabyte sequentially from a network or a disk, boom, we're shot straight into the millisecond range. Let's pivot over to Section 3, System Architecture Rules. All right, now we're getting into the essential heuristics, basically the guardrails for your system design. First rule, aggressively avoid disk seeks. Like we just saw, memory is lightning fast, but the disk is just agonizingly slow. Second, always compress before sending data. Think about it. Simple compression only costs a few microseconds, but network transfers cost milliseconds. You always want to pay that cheaper microsecond price before you hit the internet. And third, geography dictates speed. Data centers are physically bound by the speed of light, which makes cross-region data transfer inherently unavoidably expensive. Another absolute must-know rule revolves around high availability, what we famously call the pursuit of nines. This is governed by your service level agreements, or SLAs, which formally guarantee your uptime. The major cloud providers usually set their baseline SLAs around 99.9% uptime. But notice how every additional 9 you tack onto that number exponentially shrinks your margin for failure. This grid lays it out perfectly. It shows the real-world impact of adding those extra 9s. If you guarantee 99% availability, well, you're tolerating about 3.65 days of downtime a year. That's basically a long weekend. But check out that bottom row. If you push for a 99.99999% SLA, your margin of error shrinks to just 31.5 seconds of downtime for the entire year. 31 seconds. That is barely enough time to sneeze, let alone reboot a crashed server. So you really have to ask yourself, is the massive engineering cost of that extra 9 actually required for your specific use case? All right, time to put this into practice in Section 4, Real-World Application. I want you to think of every single system design problem as this sort of estimation engine. Basically, every interview question is just asking you to turn these 3 specific gears: data volume for storage, availability for reliability, and latency for speed. By turning those gears, you can calculate the required output metrics. Things like your queries per second, total storage needs, cache size, and the raw number of servers you'll need to actually keep the lights on. So let's actually run this engine using Twitter's architecture as our test case. First things first, we've got to lock in our assumptions. Let's assume 300 million monthly active users, and say 50% of them use the app daily. We'll say they post about 2 tweets per day on average. 10% of those tweets contain media, and we've got a mandate to store this data for 5 years. As for the data footprint itself, a basic tweet ID and text is about 200 bytes, but that media attachment, that's a heavy 1 megabyte footprint. Okay, let's see how this actually builds out our throughput estimate to find our queries per second, or QPS. Step 1, 300 million users times 50% gives us 150 million daily active users. Simple enough. Step 2, at 2 tweets a day, we're looking at 300 million total tweets daily. Now, step 3 is where we get to do that aggressive rounding we talked about. 300 million divided by 24 hours, divided by 3,600 seconds. Look, we don't need exact decimal points here. It rounds cleanly to a baseline of about 3,500 queries per second. And if we assume our peak load is double the average, then our peak QPS is roughly 7,000. Boom, done. Following that exact same structure logic, let's figure out our 5-year media storage. Step 1, take those 300 million daily tweets, multiply by our 10% media rate, and we get 30 million media tweets a day. Step 2, multiply that by our 1 megabyte average media size, which yields 30 terabytes of brand new media generated every single day. Finally, step 3, 30 terabytes times 365 days times 5 years. Once again, aggressive rounding is our friend, bringing us to roughly 55 petabytes. Notice how clearly tracking our units completely saves us from getting tangled up in the math here? Which brings us to our final stop, Section 5, the ultimate goal. Here is the absolute overarching truth you need to remember. Back of the envelope estimation is all about the process. Honestly, solving the problem step by step, doing it out loud, and clearly documenting your constraints is infinitely more important than arriving at some perfectly precise mathematical result. If you just clearly document your constraints and your logic, you're gonna earn that stamp of approval even if your final math is a little off. Why? Because your peers and your interviewers are really just testing your underlying logic and seeing if you actually grasp those foundational heuristics. So as we wrap up this explainer, you are now fully equipped with the heuristics, the hard numbers, and the process. But I want to leave you with one final question. During your next massive system design challenge, are you going to get bogged down trying to be a perfect calculator? Or are you going to step up, trust your logic, and act like the architect? Thanks for joining me today, and keep building great systems.